Welcome to Mrs. Z's Chemistry AP version. This is the problem worksheet titration concepts, and here we're going to start with problem 9. Here we have 10 milliliters of a sample of 0.1 molarity hydrochloric acid, and it's reacting or titrating with 0.1 molarity of NaOH. So we can see that in the analyte is the ACl because the graph is the HCl because the graph is acidic that's starting out with. So problem 10 actually asks you to write a balanced molecular and net ionic equation for the reaction. This right here is the molecular equation, molecular meaning it's not just the ions. So when we split this up in ionic equation, the chlorines get to cancel and so do the sodium, so we're left with just H plus OH turns into H2O. The H2O is liquid, so it would not be included in an ice table. And that's all we have in the ice table is our hydrochloric acid and our sodium hydroxide, mainly the H plus and the OH. So in problem 9 here, it's asking us to calculate the pH at various points in the titration and enter your answers in the data table provided, plot the points on the titration curve. So the first one is before we've added any sodium hydroxide. So all we have is 10 milliliters of a 0.1 molarity hydrochloric acid. Well, because HCl is a strong acid, the concentration of HCl equals the concentration of H3O or H plus. So then just the negative log of the H plus concentration, which is the 0.1 up here, that is going to equal a 1. And so that your pH is 1 to begin with. But now, what if we add in 2 milliliters of sodium hydroxide? Well, we're going to fill out an ice table. You can see here's the reaction. All we care about is the H and the OH here. We're going to fill out a rice table in moles. So initially, we have 0.1 molarity of HCl, and 10 milliliters is 0.01 liters. When we multiply that, we get 0.001 moles. So that is for this. Then the hydroxide, we have 0.1 molarity, 2 milliliters have been added, so this gives us 0.0002 moles, and that goes here. Hydroxide is the limiting reactant, so that is all that we can react, so we're going to subtract that amount from both sides here, from both the hydrogen and the hydroxide. Of course, we no longer have any hydroxide, but now we have this. If you remember, this is in moles, so moles divided by liters is molarity. So we take 0.0008 moles. The liters must come from now our total volume. We originally had our 10 milliliters of hydrochloric acid, and then we've added 2 milliliters of sodium hydroxide. So basically we are adding this, and that gets us, I'll go back to red, that gets us 0.012 liters. So when we multiply this, our molarity is 0.0667. This is the molarity of the H plus, because in order to find the pH, the negative log of the hydrogen, the concentration of the hydrogen ions, oops, we'll do brackets here, that is equal then to 1.18. So that's what we have here. So now the next block we need to do is 8 milliliters, and that's for this one. Our initial is the same. We initially still have our 10 milliliters of the hydrochloric acid. Now we have this for our sodium hydroxide. That is still the limiting reactant. So we still use up all of that. And now we have left over only 0.0002 moles of H plus. And now the total volume is 18, our 8 plus the original 10 here. So we have 0.0002 moles of hydrochloric acid divided by the 0.018 liters. that gets us 0.0111, you could round it wherever, of molarity. I would say at least 3 non-zero digits here though. Molarity of our H+, which is the same as the hydrochloric acid, and then the negative log of that gets you 1.95 for pH. All right, so now we have 9.9 is how much we're adding. We have 0.001, and then we're going to have 0.00099. This is still the limiting reactant, only by a tiny amount though. We're going to subtract 0.00099. So now we have 0.1234 and then a 1 and 0 here. So our moles is 0.0001 moles of H plus left over after we have reacted all 9.9 milliliters of the sodium hydroxide. And our total volume is now the 10 plus 19.9, which is 0.0199 liters. Our molarity is this, and that's of the H plus or hydrochloric acid. Take the negative log of that, and the pH is now 3.30. So when we calculate for 10 milliliters, what this ends up giving us is the same value for both. So it looks like from our ice table, 0.00 moles, 0.00 moles. Well, they both completely run out, right? So it looks like we have 0 of each. However, looking from the graph and just knowing that we have a strong acid, strong base, the pH at the equivalence point is going to be 7. So here's your equivalence point. So we're just going to write in 7. The calculation gets kind of funky because of the ice table turns into just zeros there. All right, now after the equivalence point, now we have, as we're continuing to add sodium hydroxide, we've used up all of our HCl. Therefore, all we have is sodium hydroxide left. So that's why we are turning into a more and more basic pH here. So let's go ahead. We originally still have only this amount of moles of H. And now when we take our molarity, or still the 0.1 molarity of sodium hydroxide times the 10.5 milliliters, that gives us 0.00105 moles. That's just still molarity times liters is equal to moles, just from our molarity equation. So now the H plus is the limiting reactant, and our OH is in excess. So we're going to have 0 of this left over, and we're going to have, I'll do this in scientific notation, 5 times 10 to the negative 5 moles. Oops. There's our moles, and this is of hydroxide. The volume of this is now the original 10 plus 10.5, which gives us 20.5 milliliters, or 0.0205 liters. And then this molarity is 0.002439. That is molarity of the hydroxide. So when you take the negative log of that, negative log of hydroxide is equal to POH. So negative log of 0.002439 is 2.613. 14 minus POH is equal to pH, and that is 11.39. Okay, we'll do one more, and this is adding 12 milliliters total of sodium hydroxide. The initial is still here, and this initial, let's go ahead and multiply our it's 12, 0.012 liters times the 0.1 for sodium hydroxide molarity, and that gives us 0.0012 moles of sodium hydroxide. We use up all of our hydrogen. We have 0 of this, and now we have 2E negative 4. So 2E negative 4 moles of hydroxide. The total volume now is 0.022 or 22 milliliters. The molarity then is 0.009091. Take the negative log of that, and that gets us POH, which is equal to 2.041. Then 14 minus the POH is 11.96. And there we have 11.96. All right, so then question number 12 is asking us, based on your answers to the last question, which was talking about the two pieces of evidence that this is the equivalence point, briefly explain what will determine the pH at the equivalence point in an acid-base reaction or titration. So what's going to determine is the moles of acid is equal to moles of base, but that's not always going to be 7. For a strong acid and strong base, that will be 7 because the salt of a strong acid and a strong base is neutral. But the pH is also going to be determined by the strength of the acid, because if you had a strong acid and a weak base, then you're going to have a salt that is not neutral, and that's going to change the pH at the equivalence point.